And so we have the most likely oxidizer. Let's put that up here. Is this. What's this one here? This called? Nitrate? Yeah. Plus 4 H pluses. The 4 H pluses are going to take 2 of the oxygens off that. Plus 3 electrons. This is going to go to nitrogen monoxide or nitric oxide gas. Plus 2 H2O liquids here. And so we call this the OA. And this is called a half reaction. And the jargon takes some time to get used to. You've heard of oil rig? Oil rig, what does it stand for? Does anybody know? Oil stands for oxidation is loss for electrons. Rig stands for reduction. Yeah, is gain. So we have oil rig. And so this is called the reduction half reaction. So what we have here is we have nitrate and H plus. You know, this is our 1 cup of sugar, 4 cups of flour type recipe. And this is an oxidizer. And what do oxidizers do? They oxidize things. They oxidize other things. They don't oxidize themselves. So this is not an oxidation half reaction because an oxidizer does not oxidize itself. Oxidizers oxidize other substances. It's like if you're a professional, if you're like a professional thief, electron thief, then you don't lose them yourself. So you wouldn't be robbed of electrons. You take the electrons, and so oxidizers take the electrons in the process, and that process is reduction. Now we know the conjugate relationship. On the left side are the oxidizers. On the right side would be the reducers. And so in this case, NO and H2O, this is the reducers, or RA, reducing agent. And that would be the conjugate. Mm-hmm.
So this is nitric acid, and then we just have 3 floating electrons.
No, you don't have 3 floating electrons. So this is nitric acid, but these electrons have to come from somewhere. We don't have a bottle to feed electrons. These are not like fish, and you're feeding the fish with electrons out of a bottle, a reagent bottle. These electrons have to come from somewhere. And so where do they come from? Because free electrons are very unstable. You know, you generate just a little bit of free electrons, let's say walking across a carpet or something with rubber shoes or doing something else, you know, and you can have static electricity. It's unstable. Static electricity is unstable. It wants to discharge. And so those electrons have to come from somewhere. That's why they call it a half reaction, because it's incomplete. You know, you just can't have free electrons. So, getting back to this, so this oxidizer is fairly strong. You know, it's moderately strong. That means this reducer must be, weak. And so NO is not a great reducer. Reducers, the way we think of reducers is we think of this reverse reaction occurring. And so if we go backwards here, then the NO is going to lose electrons and gain some oxygens in the process. When it loses the electrons here, it's going to form NO3 minus. It's going to lose 3 electrons. So here, the reverse process is called the oxidation half reaction. The forward process is called the reduction half reaction, and they're different species doing it. So, and so we're going in the forward direction here. This would be the reduction half reaction. If we went in the reverse direction, this would be the oxidation half reaction.
Why is it called a half reaction?
Because the electrons have to come from somewhere other than free.
So is there like part of it is missing, like other?
The other half is missing. So where is the nitric acid going to take the electrons from? And the strongest species, strongest reducer present was copper metal. Metals in general are electron rich, but some metals are more rich than others. For example, lithium would be the, and that would be the richest. It can give its electron away very freely. However, things like gold is not rich. Even though gold, has that rich connotation, gold is not rich because it does not give up its electron easily. And so gold is very, very difficult to oxidize. And that's why gold retains its luster, because there's very little that can oxidize it.
And then, is it like a property of metals that they can easily give up their electron?
Yeah, some more so than others. Yeah. And so, that's one of the properties of metals. Metals tend to lose electrons when undergoing chemical reactions. And so one of the periodic properties based on the periodic table is the left side loses electron, right side gains electrons. Left side are reducers, right side are oxidizers. That's the general property. But some are better than others. Looking at the periodic table, cesium would be predicted to be the best. Cesium is not on our chart. But things like gold has a hard time losing those electrons. Gold is a great metal. It has other metallic properties that are quite nice, like excellent electrical conductivity. So that's why gold is used in electronics, because if it's a resistance to corrosion. If you look at copper contacts, like I have an old flashlight with copper contacts, it's completely corroded. If those were gold contacts or gold-plated contacts, it would just be just like new. They stayed new and have a what do you say, lustrous surface to them. Copper, fresh copper looks good, but copper rapidly loses that nice color. And so what happens with copper is we have to reverse the equation in the book. Copper is a reactant, not a product. And so what I did was I took the reaction from the book and then just flipped it around so I have the oxidation half reaction. So if I go back to the redox chart here, and I took a look at copper, let's see if I can. I see copper as a product. I don't want copper as a product. My copper should be a reactant. So what I have to do is I'm going to flip this. So this is a reduction half reaction. I'm going to flip it so it makes an oxidation half reaction. And so I'll make copper a reactant, not a product. And this is going to go to copper 2 plus 2 electrons. So here's where the electrons are going to come from. This is a potential source of electrons if there's a driving force for this particular reaction. Now, nitrate wants 3 electrons. However, copper only gives up 2 electrons. And so what we're going to need is we're going to need more copper. So what if I double the copper? So I have twice as much copper. If I double the copper, then what's going to happen is I'll just multiply by 2. 2 times 2 is 4, so I'll get 4. 4 is too many. Nitrate only wants 3. And so what I'm going to do then is I'm going to double the nitrate. So if I double the nitrate, I'm going to get 2, 8, 6. Well, 6 is too many. So I'm going to triple the copper. And if I triple the copper, then I get 6 electrons here. So we look for the, in other words, we just cross multiply. That's the easiest thing to do. And so if I cross multiply here, this first equation by 2, and that's 2 times 4 is 8, 2 times 3 is 6, 2 and 4. Then this gives me 6 electrons that are consumed, and then I'll do 3 here, 3, 3, and 3 times 2 is 6. So we need this. This is a critical step because the free electrons are very unstable, and we have to make sure that the electrons gained is equivalent to the electrons lost. All right, then what we do is we combine these two equations next. And so we end up with 2 nitrates plus 8H plus 6 electrons plus, I add everything on the reactant side, plus 3 copper solids. And then I'll add everything on the product side, 2 NO gas plus 4 H2O liquid plus 3 Cu2 plus 6 electrons. And then, like going from a ionic equation to a net ionic equation, we cancel out the spectators. So the 6 electrons aren't really a spectator. I mean, they're consumed and they're lost, and so they're transferred. But since we have 6 electrons on the left and 6 electrons on the right, I'm going to cancel those. And then what else can I cancel? It looks like that's it. And so I'm going to rewrite this equation. But before I do that, before I invest a lot of work, I want to make sure there's a driving force, because if there's no driving force, then we'll just say NR. And so the driving force is we do this from this. And so what was this reaction? This is another half reaction here. But this half reaction just do this. Is the oxidation half reaction. So oxidation is loss of electrons. So what did copper do? Copper lost electrons. 3 moles of copper lost 6 moles worth of electrons. So that's the oxidation half reaction. So who oxidized copper? Who oxidized copper is nitrate. Oxidize the copper. And so oxidizing agents oxidize things. So the thing that oxidizing agents oxidize, these are called reducing agents. And so my reducing agent is copper. And then we have our conjugate oxidizing agent over here. Copper's not the greatest. You know, the coinage metals aren't great. Copper, nickel, silver, gold. You know, the coinage metals are coinage metals because if they use like iron, let's say they made quarters out of iron, they'd rust away. You know? And so the coinage metals are not great reducers. In other words, they're pretty stable metals. So what we do here in this reaction, before I get too far, I'm going to label this over here. This is my oxidizing agent on the left. This is my reducing agent on the left. And then on the right, this will be my reducing agent, and this will be the oxidizing agent. And then what we do is we compare the two oxidizing agents, nitrate in acid versus copper 2 plus. And so we just go back to the chart and take a look. Which one is stronger? Yeah. So we can see nitrate in acid is here. And then I see copper 2 plus is here. So what we're doing is we're going downhill. I used the zigzag method the other day. You know, there are different ways you can do this. I didn't chopped off that water, but it's all right. So we can just use the chart directly. Oh shoot, I forgot to do something here. Just insert a text box. So, okay, actually this is going to let me do this really quick. So if we have nitrate and H plus react with copper, then what forms? So this is the zig part, and then what forms is the zag part. So we're going to form copper 2. So when we compare nitrate and H plus versus copper 2, we're going from a stronger oxidizer to weaker oxidizer. That's the first zag. The second zag is for the reducer. We want to go from a stronger reducer to weaker reducer. And so the second zag is this. Nitrate and H plus is going to form NO and 2 waters. Cut off there. And then we're going from, which one's stronger, copper or nitric oxide and water? As a reducer. Copper. This is a stronger reducer. This is a weaker reducer. That's because the reducers are flipped upside down. What were the two things that you have to memorize? Yes, lithium solid is down here. And fluorine or fluoride? Not fluoride. Fluoride is quite stable. Fluorine. There's a huge difference between fluorine and fluoride. People brush their teeth using sodium fluoride. You go to the dentist, they'll give you a fluoride rinse. Not supposed to drink anything or eat anything like 30 minutes after, right? But if they gave you a fluorine rinse, it would be disastrous. Potentially. I was working with fluorine gas when I was a student at UCLA, and I was thinking, am I going to die? Because my advisor there showed me the fluorine chemist handshake. You know, the fluorine chemist handshake, the first year you go to the conference, it's like this, you know. And then each successive year, it goes like this, and then like this, and then like this, and then, how you doing? And then you have to retire after that, you know. So fluorine chemists have a short life. Yeah, so I was taught, if there's ever a fluorine leak, the fluorine was contained in a 1/4-inch steel box. And if there's a fluorine leak, then it's contained in the 1/4-inch steel box, so you run away, and hopefully it eats through it slowly, so you can survive the fluorine leak. These are all kind of tales, urban tales. But then I started researching it more, and they got a group of volunteers, Army volunteers, to walk inside a cloud of fluorine gas with a jar and a lid. And they were told to walk in as far as you can until you can't stand it anymore, and then seal the jar. And then they brought those back and analyzed it. And so they didn't die, fortunately. So after that, I felt a little bit more comfortable working with fluorine. This was in the 1950s. I don't think they do that nowadays. I mean, it would just seem unheard. Uh-huh.
Gain electrons, so that's why I thought it would be the strongest.
Fluorine is the strongest oxidizer.
Oh, did I say fluoride?
You said fluoride. Fluoride is its conjugate. If the fluorine is the strongest oxidizer, then fluoride must be the weakest reducer. It's a weak reducer means it's very hard to strip the electrons off of. But fluoride has other potential reactions. We have 3 potential reactions for fluoride. One is redox. Redox, it's nothing. We kind of ignore it because it's so unreactive. Metathesis is very reactive because fluoride loves calcium. And our bodies are full of calcium. You have calcium in your blood. You have calcium in your teeth and bones. And so fluoride is not good for your health. It's a health risk, and in high concentrations. There are people trying to ban fluoride. Have you heard? There are people who are trying to ban fluoride out of water and other things. They say it causes issues with your brain. I'm not sure what the reactions are. But, fluoride's going to upset the calcium balance in your body anyway. In fact, they have things, they have injection kits of calcium. Did I tell you? Yeah. Also, fluoride's a weak base. So the acid base and the metathesis, probably the metathesis properties are the most significant of fluoride. The redox properties are nothing. Uh-huh.
Could you go back up? So I wouldn't say
Okay.
so you're saying that, like, the copper solid turning into the copper 2 ion, or those 2 electrons, which means that it's oxidized. It was like the other half of the reaction was the oxidizing agent.
This is the oil part of the reaction. This is the rig part of the reaction. We need oil and rig for a reaction to occur.
But in the net ionic equation, you said that nitric acid was the oxidizing agent?
Yeah, okay. The nomenclature for redox terms is often confused. Let's say you're a professional bank robber. If you're a professional bank robber, do you get robbed or do you rob others? You rob others. And so if you're a professional oxidizer, do you get oxidized? No, you get reduced. You gain rig. Rig is gain. You gain electrons. Your rig. And so it's often confused, but it's just repetition. Eventually it'll just click and it'll be super easy, but before then it's difficult to remember. Well, anyway, we know that this is stronger, this is weaker, and this is stronger, this is weaker. It's always got to go strong, strong, or weak, weak to the other side. So in theory, we only need to do one, but we do both just as a double check to make sure. And sometimes it's easier to do the oxidizer, sometimes it's easier to do the reducer when you're looking for speed. If I was looking for speed, I would only do one, whichever one's easiest to look at or figure out. Sometimes you aren't given the chart and you have to figure it out based on your database of knowledge in your brain. You can make a prediction. Well, okay, this reaction is go. So we have driving force. DF stands for driving force. Since the driving force is present, I'm going to rewrite this. If a driving force wasn't present, I wouldn't waste my time rewriting this. I'd go on to the next question. Now, there's going to be some changes. And so what types of changes do we see? Nitric acid, this is colorless. This is a CCS. And then copper metal, you know, that's just kind of a brown gold. What would you call it? Orange metal? Just say orange solid. NO is a CCG. Do you know what a CCG stands for? Clear colorless gas. H2O is a CCl. What does a CCl stand for? Clear colorless liquid. However, when there's copper present, it's no longer CCl. Do you know what color copper 2 is in water? Not green. You need it in high enough concentration. No. Blue. You might have seen it. If you put ammonia in there, you'll definitely see it, but it is a very light blue color, but at higher concentrations, it darkens. Now, what we have here is after this reaction occurs, a second reaction happens. And this is called a consecutive reaction, right? In which the NO gas is further oxidized by O2 in air to form NO2 gas. And so we can balance this. This is 2 NOs. So this is like, you know, complete combustion or something, although it's not totally complete. For complete combustion, what should nitrogen be? If we look at the oxidation states, what's the oxidation state of nitrogen in nitric oxide? +2. Oxygen is -2. What is it in nitrogen dioxide? +4. +4, is it maxed out? No. But this is pretty much maxed out in air. This comes from air. If there's no air present, we'd get a CCG. If there's air present, then we get this brown gas. Have you seen smog? What it looks like? This is the brown gas in smog. Smog used to be much more common in Los Angeles. I remember when I was young, coming to Los Angeles, it was always smoggy, this brown haze all the time. You can still see the brown haze. If you go out to the ports, you see it from diesels. Primarily diesel exhaust gives it. So let's take a look at this reaction. Just pick one of these videos here. Oh, this is good. This Royal Society of Chemistry has some great videos.
Using a reactivity series is so that you can later on develop this into the electric acid in a bunch of dissolved protons. Round bottoms is preferable, as you can see the reaction better.
Looks like they
but
have
if you
some
need to
nitric
get a thick
acid in
walled
this
or
Florence
silicate
flask, and
flask,
they just
a
put
Butler
some
flask
copper
may be
metal
a suitable
in there.
alternative.
You can see what color. Well,
Immediately we begin to form
NO2
NO2 gas above the copper nitrate that's formed.
You see the brown gas?
I've got a delivery tube here that's feeding into a
NO2.
1 litre flask of water.
Well, they're going to take the NO2.
The glass wall is there to minimise
Oh,
diffusion of
they're
any
taking
of the
NO2 and
toxic
mixing it with
NO2
water.
that doesn't dissolve, and as such you can perform this experiment without the use of a fume cupboard. As the reaction cools, the gases inside the flask will contract, drawing some water back from the conical flask. This is where additional steps have been taken to minimise risk. There's a small chance that the reaction flask could be damaged by the rapidly changing temperatures which follow the addition of the water. As such, if this experiment is performed in the open lab, both students and the demonstrator should be protected by safety screens. A trough or bowl is placed underneath to contain the mixture in case of any leaks. I've placed a small LED light in mine to help the camera pick up the colours.
Talk about that, but take a look at the reaction. That reaction was pretty rapid. And then you see as the concentration of the copper 2 ions
the gases inside the
gets
flask
higher.
will
What color is copper 2 there? Do you see that? Blue. Do you see any copper metal left? No. The copper was a limiting reagent here. They had excess of nitric acid. And then you see this brown cloud here. Brown cloud. I was once driving on the 101 freeway and I got stopped because a tanker truck flipped on its side. And it was spilling out a whole bunch of acid. I was like the first car there, and the news team pulled up right in front. So I was watching the news anchor, or not the news anchor, but the reporter, talking about the acid spill. And he said, "Oh, you know, there was a hydrochloric acid spill." And then I was just probably had like Chem 4 by then, but I thought, no way, that's not hydrochloric acid. You know, that's got to be nitric acid because there's huge plumes of this gas coming off, just fuming off there. Anyway, hydrochloric acid won't do this to copper, nitric acid. And so this little scrubber here is trying to take advantage of another type of reaction, which we'll talk about. And so if there's no air, we aren't going to get NO2. It would just be a CCG. But since there's air present, we get the NO2. And then in that particular reaction there, they're doing one more reaction. And the one more reaction is quite simple. So this is a redox reaction here. But the next reaction that they're doing is an acid-base reaction. It's a Lewis acid-base reaction, in which we take NO2 and H2O. And do you know what this forms? Maybe this is going to be a redox reaction too. This is going to form HNO3. HNO3.
Do you think it would be better to write it as like HOH?
H plus and nitrate?
No, like writing it as like HOH, like if it was hydroxide.
Oh yeah, sometimes. That's good for Bronsted, but this is not a Bronsted. This is actually redox too. How do I know this is redox? How can you tell this is redox? Because if we start off with NO2, NO2 has nitrogen in the +4. But NO3, what's the nitrogen in NO3? +5. So this is also a redox. Sorry, this is not acid-base. I was thinking this is acid-base. Well, since we're doing this, what I'm going to do is this. We're going to figure out this reaction using skeleton redox. So we're given the major product. If we're given the major product, then we could figure it out. In skeleton redox, we split into two half reactions, two skeleton half reactions. And so we look at NO2, and where did the NO2 end up? The NO2 ended up in NO3 minus. So this is called a skeleton half reaction. The H2O, we'll figure it out. We do it by steps. Ends up in question mark. But the thing with skeleton redox is we kind of ignore the H pluses. This is why I didn't even do the H plus, because of the methodology. The methodology, we don't have to worry about H plus, and even like something like oxygen and hydrogen like this, we don't have to. That's why I put a question mark there, because in skeleton redox, what we do here are there's certain steps. Step 1, we balance all elements other than hydrogen and oxygen. And so over on the left I have one nitrogen, over on the right I have one nitrogen. And so the nitrogens are balanced. Okay, over here there are no other elements other than hydrogen and oxygen. Okay, then we do this in a sequence here. We balance out the oxygens next. And so over here on the left I have 2 oxygens. Over here on the right I have 3 oxygens. So the oxygens aren't balanced. But I don't balance the oxygens by adding O. Do you know how I balance the oxygens? I balance it by adding, not hydroxide, water. I balance it by adding H2O. And so that gives me a total of 3 oxygens. 2 oxygens from NO2 and 1 oxygen from H2O. Then now check. The next step of this is I balance out the hydrogens. So I total up all the hydrogens on the left. I have 2 hydrogens. And then over on the right I have 0 hydrogens. And so do you know how I balance out the hydrogens? I'm sorry? Yeah, plus H. Plus H plus. I add acid. Okay, then I balance out the charge. And so NO2 is neutral, H2O is neutral, so I have 0 charge on the left. On the right, I have NO3 is -1 and H plus is +1. And so that gives me -1 and +1 gives me 0. And then I realized I did something wrong. How many hydrogens do I need? I need 2 H pluses, sorry. So this should have been 2 H pluses. And therefore it doesn't add up to 0. What does it add up to? It adds up to +1. On nitrate. Nitrate normally has a -1 charge. So how do I balance out the charge? How I balance out the charge is by adding electrons. And so how many electrons do I need? I need 1 electron on the right. And so the +1 will be canceled out by the -1. And so this gives me my half reaction. NO2 plus H2O yields NO3 minus plus 2H plus an electron. Now I want to check that it's balanced. When we balance these things, we have to balance it 2 ways. The first is to make sure the atoms balance. Whenever we have redox, we got to do an atom balance followed by a charge balance. And so I have 1 nitrogen, 2 oxygens plus 1 oxygen gives us 3 oxygens. 3 oxygens here, 2 hydrogens, 2 hydrogens. So the atoms are balanced. Then I've got to make sure the charge is balanced. This is 0 plus 0 is 0. Minus 1 plus 2 is plus 1. Minus 1 is 0. And so the charges are balanced. So this is what we call a balanced half reaction. Now, is this an oxidation half reaction or a reduction half reaction? Is this oil or rig? What does oil stand for again? You have to be careful. Oxidizing means you're the oxidizer. So it's got to be oxidation. Oxidation means, does that make sense? And so this is oxidation is loss. So NO2 is losing an electron, you know, because nitrogen is going from plus 4 to plus 5, so it's losing electrons. So this is oil, and so we call this the oxidation half reaction. Where did that electron go? The electron must have went to the oxidizer. So if NO2 was oxidized, then there must be an oxidizer that oxidized NO2. So NO2 and H2O are called our reducing agent. And so we got to figure out what the oxidizing agent is. NO2 is a gas, H2O is a liquid. And so the oxidizing agent, well, let's take a look over here. H2O. Is that it? And so we look here. We balance out the oxygens first. So we have 1 oxygen, 0 oxygens. And so we add an H2O. And then we balance out the hydrogens. We have 2 hydrogens here. And over here we have 2 hydrogens here. And so that's balanced. And then we balance out the charge. They're the same charge. So, so what gives here? H2O goes to H2O. Is that anything? No, that's nothing. That's not going to work for us, unfortunately. And so what we're going to do here is this. We're going to go from H2O to H+. But going from H2O to H+ is not going to work for us. Maybe. We'll try it and see what happens. And so over here I have 1 oxygen. Over here I have 0 oxygens. And so I'm going to add 1 H2O. And then I'm going to balance out the hydrogens. So over here I have 2 hydrogens. Over here I have 3 hydrogens. So I'm going to add an H+ over here. And then what? Then charge, but the charges are the same, so it's balanced. So now I have H2O plus H plus goes to H2O plus H plus. So charge is missing. So it looks like water is not going to be it. We have to think of something else that might do it for us. And so what else might be present? We got to think of an oxidizer. Is water a very good oxidizer? No, water is not a very good oxidizer. Can you think of an oxidizer that might be present? All they're doing is they're just bubbling. The NO2 through water. And so the only other oxidizer that we can think of that could be present is oxygen. And so we'll go, O2 goes to question mark. I don't know what the product is. We'll try this. Maybe oxygen plays the crucial role here as the oxidizer. And so we have 2 oxygens here, we have 0 oxygens here. And so we'll add 2 waters. And then we'll have 0 hydrogens over here and 4 hydrogens here, so we need plus 4H plus. And then we have 0 plus 4 gives us plus 4, and then the waters are neutral, so that's 0. And so we'll need plus 4 electrons here. Let's try to add it up. And so this is going to give us O2 plus 4H plus 4 electrons yields 2 H2O. H2O is a liquid, O2 is a gas. And so let's check if this is balanced. So I have 2 oxygens. And then 2 oxygens over here, 4 hydrogens, and the net charge is plus 4, minus 4 is 0, and this is 0. So this is a balanced half reaction. Is this an oil or is this a rig? Is this an oil or is this a rig? This is a rig. If you have 2 oils, will 2 oils work? No. If you have 2 oils, something's wrong. If you have 2 rigs, will that work? No, you need an oil and you need a rig. And so this is the rig. And anyway, reduction is gain. So we call this the reduction half reaction. All right, now we have our oil and we have our rig. And our next job is to just add them up. Over here, our oil loses 1 electron. Our rig gains 4 electrons. So I'm just going to cross multiply here. I'm going to multiply this one by 4. We have 4, 4, 4, 8, 4. And so now they cancel out or balance out. And then I'm going to combine these 2 equations here. So I have 4NO2 plus 4H2O. That's from the top reaction. From the bottom reaction, I'll have plus an O2 plus 4H plus 4 electrons. Okay, and then the products, I'm going to combine 4NO3 minus plus 8H plus 4 electrons plus 2 H2Os. Before I get too far, I'd like to see if there's a driving force for this. But when I do that, can I use the chart for this particular one? And the answer is I can't use the chart because I know the chart. I'm quite familiar with the chart. And NO2 is not on our chart. So I don't have this. There is something that's similar to NO2. What is that? No. I mean, nitric acid is somewhat similar, but there's something else that's even more similar, I think. No. No. It is, what is this called? It's not called no, but it's called nitrogen monoxide or nitric oxide. This is called nitric oxide. Nitric oxide is, you know, are you guys familiar with the Ick-Aus convention? The Ick usually refers to the higher oxidation state. The Aus usually refers to the lower oxidation state. The Aus. So let me just do this on this side. So the problem is what if you have more than two? And then it kind of fails.
You have N or 2.
Right. And so it kind of fails. So let me just do this on the side here. NO is AKA nitric oxide. You know, most people call it nitric oxide because nitrogen monoxide is too long, cumbersome. And most people don't call this dinitrogen monoxide. Do you know what most people call this? They don't call it dinitrogen monoxide because it's just too long and cumbersome. They call it nitrous oxide. And so the Ick refers to the higher charge. This is the higher charge is +2 in this case, but that's not the highest charge. What's the highest charge on nitrogen? +5. And the Aus refers to the lower charge. What's the charge on nitrogen and nitrous oxide? +1. So nitrous oxide, many people are familiar with nitrous oxide because it has another name. What's the other name for nitrous oxide? Laughing gas. Nitrous oxide is called laughing gas.
Do you have to know, like, the common names? Like, do you have to know that acetic acid is going to be?
Yeah, you have to know acetic acid. Nobody calls it ethanoic acid. Ethanoic acid is its systematic name, but nobody ever calls it ethanoic acid. I don't know how many people call it this. Most people call this nitric oxide. Nitric oxide, you know, both of these are kind of pollutants. You know, oxides of nitrogen. Nitric oxide is a pollutant, but nitric oxide has a biological role. One of these, maybe not a chemical messenger, but a lot of people are looking for like nitric oxide boosters for cardiovascular health.
Sorry, can you go up a little bit so I can see the full read off?
Oh, so I'll come back right to it, but. According to Science Magazine, nitric oxide was named Molecule of the Year in 1992. Okay, so you could read about it if you want. It has a really important biological roles that really weren't well understood. And then, you know, I mean, they even tried nitric oxide during COVID, you know, to see if nitric oxide therapy would help with the blood clotting issues, because it's nitric oxide is important at regulating blood circulation. So we have nitric oxide. What would be a better reducer? Reducers lose electrons. Reducers are oxidized in the process. So what would be easier to lose electrons? A nitrogen +4 or nitrogen +2? which one would be easier to take electrons from? A +4 or a +2? +2 is going to be a lot easier, a heck of a lot easier. Each successive electron you ionize costs you about double the amount of energy. And so, to ionize 1 electron costs this much. Ionize 2 electrons, that much. 3 electrons, it just grows and grows and grows and gets more and more difficult to ionize. And so we know nitric oxide is going to be better. So this is going to be weaker. And these are the patterns that you look for. Like, for example, NO2 is not in the chart, so what you do, you try to find a bigger chart. Try to find a bigger chart, maybe in Appendix D. Appendix D has a 5-page chart, redox chart. Or if it's not even an Appendix D chart, then you can try to find an even bigger chart, maybe in the, what's that handbook called? Or the index. It was a while ago, probably fleeting memory. Back when. Hmm? No, not the safety one, it's the database. You go to the library and, oh, I need that book, you know, that book. And they say, well, what book? That book. I need that book. Nobody remembers it? I always remember, I never forgot it. The first time I heard it, I never forgot it. And the reason I never forgot it is because of CRC. What does CRC stand for? I never forgot it because it's such a funny company. The CRC company, the CRC stands for Chemical and Rubber Company. And the book is called The Handbook of Chemistry and Physics. The CRC Handbook of Chemistry and Physics. And the index that I was talking about is the Merck index. The Merck index is from the drug company, Merck, which has been around for a very long time. So this is going to be more difficult, but this is a potential reaction, you know. What we're looking for are potential reactions, and we look for driving forces and whatnot. But anyway, we do the conjugate relationship. So if we do the conjugate relationship here, we can see possibly what it is. Maybe we don't need it, the chart. So let's take a look. If that's our reducing agent, then this will be our conjugate oxidizing agent. But I've seen nitrate and H plus as our oxidizing agent before. But the nitrate and H plus that I saw before is nitrate plus 4 H pluses yields NO plus 2 waters. And so it's a different reaction. This is going to different products, so we can't use the same half reaction for this. And then over here, our rig part, we look at oxygen here. Our oxygen and H plus, well, this will be our oxidizer. Oxidizers take electrons, taking 4 electrons. This will be the conjugate reducer. And so we might do this. We might try to compare water versus NO2. Both are probably pretty bad. We might try the oxidizer. Oxygen versus H plus. Which one do you think is stronger, oxygen or H plus? Now we form a different product, so we can't use the exact same thing. Oxygen versus nitrate and H plus, I should say. So when we look at this, here's oxygen, here's nitrate and H plus, but this is forming NO, not NO2. But we'll just go with this and say maybe it's roughly around the same, because we're forming NO, which is a stronger reducer. We're going to form an even weaker reducer, NO2. And so maybe that's even going to be more stable, so maybe it increases its rank a little bit here. Versus oxygen in H plus. This is the wrong oxygen though. We have another oxygen. We have this oxygen up here in H plus, which yields H2O. We have this oxygen down here, which yields hydrogen peroxide. So we use this one. And so it's hard to judge because we're forming NO2, which might actually help. It's forming a weaker, or in other words, this will probably require more information, but this is a potential reaction, so we're not going to complete it as written like that. What I'm going to do is I'm going to simplify this. And so, simplifying this, I have 4 waters . So what I'm going to do is I'm going to cancel out 2 of the waters on the product side and 2 of the waters on the reactant side. And then I have 4 H pluses on the reactant side. I'm going to cancel out 4 of the 8 on the product side. And then the 4 electrons will cancel like this. So overall, the reaction should look like this. It's going to be 4 NO2 plus 2 H2O plus O2 yields 4 nitrates plus 4 H plus. And I guess that's it. NO2 is a gas, H2O is a liquid, O2 is a gas, and these are aqueous. Then we check if this is balanced. We check if this is balanced by checking the atom balance first. So 4 nitrogens, 4 nitrogens, 8 oxygens plus 2 gives us 10, plus 2 gives us 12. 4 times 3 is 12. 4 hydrogens, 4 hydrogens. So atoms are balanced. And then the charge on the left is 0 plus 0 plus 0 is 0. And the charge on the right is minus 4 plus 4 is 0. And so this is balanced. We always do a check of the balance. Make sure it's okay. Well, anyway, this was a side reaction. This isn't part of the whole thing. I might have waited too late to save this. Let me pause. I'll just do this in Excel. I better save it first. All right, so let's analyze why the single replacement failed. The reason my single replacement failed is let's say you're you're the director of the play, this play, and you're assigning roles. And so you call A is the reducing agent. And you say B, you're going to be the oxidizing agent. And then X, you're going to be a spectator. And so this is fine here. So you're the director of this reaction, and you tell copper you're going to be the reducing agent. And then you go over here and you say, okay, hydrogen ions, H+, you will be the oxidizer. And then you'll say, nitrate, don't do anything. Just stay as is. And then you let the play run, and the play runs, but there's a problem. And the problem is this. Can you prevent nitrate from reacting? You need to prevent nitrate from reacting. And then you look at this chart, and you go, okay, H+, you're going to be the oxidizer, and then nitrate, you do nothing. Is that going to work? No. I mean, H+ is a much, much weaker oxidizer than nitrate. And so this is destined to fail. This is absolutely going to fail. The reason it's going to fail is because you assigned H+ as the oxidizer, but you have nitrate and H+. Nitrate and H+ is way better. And so this is misassigned. The oxidizer should have been X. But your pattern here does not allow X to react. X always has to be a spectator in single replacement reactions. And so this failed. Therefore, we call nitric acid an oxidizing acid. All acids are oxidizers. Normal acids are just H+. But there are certain acids which are stronger than H+, and that is due to the anion. The anion's electron poor. Nitrate's electron poor. And therefore, much more electron poor than H+. H+ doesn't really take on any electrons. Even with nitrate, H+ is kind of a spectator. This oxidation state doesn't change. There are other reasons we don't use single replacement sometimes. So there are more failures, of single replacement. But there are other reasons we don't use single replacement. Why don't you try this example here? Use the chart method. I'm sorry, can you read? Oh, week 6, yeah. It's week 6. If you go to week 6, there should be a link, and I don't know, was that link dead? Okay, let me fix that link right now.